So good morning everyone and welcome back. Uh, so as usual, I shall be waiting here for 2 more minutes before I start. And again, here is the agenda for today's class. We have been talking about frequency responses for a while, and today we shall try to figure out the frequency response of different circuits apart from RC series circuits that we have already done, and we shall have a different perspective on RC series circuits as well. And again, whatever discussions we had earlier, especially in our last class, that discussion is valid for any LTI system, right? Yeah, not necessarily for electrical circuits, as long as it's linear and time invariant. That discussion we had earlier in our last class is valid. Okay, about frequency responses and about the system being excited with a sinusoidal input. Okay, so those discussions are perfectly valid under any linear time invariant scenario. Okay, as long as the systems we are discussing are linear and time invariant, all the discussions we made are absolutely valid. So in any case, I shall be waiting for 2 more minutes, and again, feel free to ask any question that you might have during the stream. And just one more thing, very recently, the internet connection has become even worse than what it was already before, and it has been so happening that the internet connection is breaking quite often during the stream. Okay, I've encountered this breakage of internet connection quite often. So yeah, please stay on the stream if the internet connection breaks halfway through. Okay, um, I shall probably be able to get back. So please don't leave the stream if the internet connection breaks halfway through. So that's one request for me. All right. So again, welcome back, uh, and good morning to all of you. So without wasting any more time, let's jump in, right? So we have talked about our series RC circuit, right? And we have talked about how we configured that as a series, as a low pass filter in our last discussion, right? In our last discussion, we saw how we figured out uh, how to use a series RC circuit as a low pass filter, right? So we saw that in our last discussion. So now today, let's have the series RC circuit just as before. Okay, but now instead of measuring the voltage across the capacitor, let's measure the voltage across the resistor. Let's see what happens then. Okay, let's see what happens then. So we have the input, and now here is the capacitor for the series RC circuit, and by now I believe you people have become quite familiar with the series RC circuit, right? All right, so here I am applying the voltage here, of course. So this is C, this is R, these are the corresponding constants, this is the capacitance, and this is the resistance. Okay, and here I am applying my signal source here, so it could be any signal. Okay, all right, so that's going to be my xt. Of course, I consider inputs to be x, so that's xt. Okay, this current eventually has to be written as it. There is nothing I can do about that. And the voltage that I'm measuring across the resistor is now being considered to be yt. So yt is the voltage that is being measured across the resistor. Now previously we were measuring the voltage across the capacitor. Now we are measuring the voltage across the resistor, right? And we so far have understood that we can just replace all of these elements with their impedances, right? And the moment we replace their values with their impedances, what happens? We are essentially applying Fourier transform on the circuit, right? So let's apply Fourier transform on the circuit, and after doing the Fourier transform, let's see what we get, right? So if I take the same circuit, okay, if I take the same circuit, and now on the same circuit, if I apply Fourier transform, so if on this circuit, if I apply Fourier transform, okay, so we are applying a Fourier transform on this, and if I am applying Fourier transform on this, and then say, so this becomes x omega, of course. Okay, Fourier transform of xt is x omega. This becomes I omega, the current. This is a simple series circuit. The impedance of a capacitor, capacitive impedance, is 1 by j omega c. We know that. Impedance of a resistor is just R, because that's a scalar. That was a scalar relationship. V equal to IR, of course, from that. And this yt has become y omega. That's after application of Fourier transform on the circuit, right? So we know that, right? So of course, what is the current through this entire circuit? Because again, this is open, so there is just one loop here. So what is the current through this entire circuit? Of course, we know the current would be total voltage divided by total impedance. So I'm doing it without even applying the. So we are applying the KVL, but in any case. So what is the total impedance? Total impedance is here. The total impedance is this is R plus 1 by j omega c. All right. And what is the voltage that appears across this entire circuit? That's x omega, right? So that's the current that is flowing through the circuit, right? So that's again after application of Fourier transform, right? So there is no problem with that. So with that said, what is the voltage that appears across the resistor? What is the voltage that appears across the resistor? What is the voltage? What is the voltage that appears across the resistor? Can anybody tell me? Of course, if this is the current, then the voltage that appears across the resistor will be just R into I. Okay, so then therefore the voltage that appears across the resistor, which I denoted with y omega, okay, that would be R into I omega, right? And what is R? R is a constant, just a constant. So R into I omega, this is that thing, x omega divided by R plus 1 by j omega c. And again, just the agenda said, today we are going to learn a bit of programming. So far what I have been doing, I have been making demos using Python without actually teaching you how to do this. Today I shall probably be teaching you how to do this. Okay, and after the end of this entire theoretical part, we shall have a few practical classes, okay, using Python, and we shall learn how to practically employ Python in order to for learning this, right, for learning signals and systems, for analyzing signals and systems. Okay, because just to let you know, one of the foremost developers of one of the biggest most used libraries in Python, namely NumPy, the library that we use for doing numerical computation in Python, is known as NumPy. Okay, and the library we use to do scientific computations in Python is known as SciPy. So these two libraries, NumPy and SciPy, was developed by someone named Travis Oliphant, and that person was a signal processing engineer. So he was actually doing his PhD in signal processing. And while doing his PhD in signal processing, he actually wasted a lot of time in developing those libraries in Python, NumPy and SciPy. And today, I mean, we are kind of fortunate to have those libraries, because no one who studies scientific computing, does scientific computing, no one really can do scientific computing without using NumPy and SciPy, these libraries in Python. So yes, so we are actually grateful to a signal processing engineer. So yes, many of the good things in the world came from electrical engineers. All right, so understandably, this is the current, this is the voltage across the resistor, right? So this is the current, all right? So there is no issue with that. So if I keep on simplifying this, of course, if I just pull this up, what happens? What do I get? I get R J omega RC. So in the numerator we have that basically, and in the denominator I have 1 plus J omega RC, 1 plus J omega RC. So we have J omega RC into X omega. So that's what we have. Y omega is this. Again, what is X omega? Now we are, instead of measuring, so in the last class we measured voltage across the capacitor. Now here today we are measuring voltage across the resistor itself. Okay. So what is my frequency response? My frequency response is the Fourier transform of the output divided by the Fourier transform of the input. So this divided by this. So that gives me J omega RC divided by 1 plus J omega RC. All right, that's understood, right? So let's find out the amplitude response, right? Again, this is how the system is going to respond, right? So the idea is, if I excite this system, if this input is a sinusoid, if this input is a sinusoid, the output is also going to be a sinusoid, except for the fact that the amplitude of the output sinusoid and the phase difference between the input and the output sinusoid will be entirely determined by this function, right? Will be entirely determined by this function. So let's calculate that. So the amplitude response, which I represent with mod H omega, so that's the mod of this entire thing. Okay, mod of J omega RC divided by 1 plus J omega RC. And if I take the mod on this, that simply becomes omega RC. Okay, because omega R and C are positive constants here. We are considering positives. Otherwise, we would have to put a mod sign there. Okay, and here it will be 1 square. So that's 1 plus omega square R square C square. Understandable? Yeah, one of you asking whether this can be a DC supply. Yes, we actually did that, right? We actually calculated the step response, right? In an earlier class, like I think 2 classes before this one, we actually calculated the step response. And what is the step response? That is the response when I apply a DC. So DC supply, right? What is the step input? That's a DC input, right? So we calculated the step response of circuits like that, right? That is how we can apply a DC here. We can apply anything, right? Okay, just go back to the classes, like the class where we actually, so I think it would be the class that took place in last Friday. Okay, so go through that. So check the handouts there. We actually calculated the step response of a series RC circuit, and where of course the step input is nothing but a DC source that was applied at t equal to 0. Okay. So today we are actually checking the frequency response. So if I apply sinusoids of different frequencies, right? Because at the end of the day, any signal, okay, as long as it is bounded and satisfies the other Dirichlet conditions, any signal can be actually considered to be a composition of sinusoids, right? So any arbitrary signal can be considered to be a sum of different sinusoids of different frequencies, right? So that's the idea here. So if we can figure out how the system responds to different frequencies, if we can figure out how the system responds to different frequencies, we can actually figure out how any signal, how the system would behave to any input signal, right? Because any input signal, as long as it satisfies the Dirichlet conditions, has a Fourier transform representation. And by that, we can say we have a representation of the circuit that tells me, we have a representation of the signal that would tell me what are the different frequency components, different frequency sinusoids present in the signal itself. What are the amplitudes of those, what are the phases of those, and so on, right? So we get to know that. And if we know how the system behaves with every individual frequency present in the input signal, then we know how the system would behave with that input signal, whatever random input signal I have, right? Because if I know the behavior of the system with every single frequency constituent components in the original input signal, then we know how the system is going to behave with the signal itself, entire signal itself, right? That is why we study frequency responses, right? Because any signal at the end of the day can be actually decomposed into many sinusoids, right, of different frequencies, right? And so if I know the behavior of the system with each of the individual component sinusoids present in the signal, present in the input signal, we know what the output signal is going to be, right? So with that said, this is the frequency response, right? This is the amplitude response. And what about the phase angle? Angle of h omega. And again, this discussion is completely bordering on what we studied in the last class, right? And again, this is going to be the angle of this entire thing. Angle of j omega rc divided by 1 plus j omega rc. So again, from the principle of argument here, we have angle of j omega rc. So angle of j omega rc minus angle of 1 plus j omega rc. That's true for complex numbers. Again, we would have a plus minus n pi. I'm not writing that because I'm not going to go beyond the principal argument value here. So that's again theory for complex numbers. Again, this is a purely imaginary number with a positive imaginary part. So this is the imaginary part, purely imaginary number with a positive imaginary part. You can assume as if the number is somewhere here on the imaginary axis, somewhere here. So the angle would be pi by 2. This has an angle of pi by 2, right? This is a purely imaginary number with a positive imaginary part. This is the imaginary part, omega rc. So the angle would be pi by 2. So it has an angle of pi by 2 minus, and this is just a complex number, and this is probably in the first quadrant because 1 is positive and omega rc is also positive, considered to be positive. So the angle would be tan inverse y by x, where y is the imaginary part and x is the real part. So that's going to be, let me just write it here. So that's pi by 2, and this is minus tan inverse omega rc. All right. So let's copy this circuit once again. Let's have this circuit here. Let me copy this circuit. So what we have calculated so far is this, that if I take this circuit, okay, if I take this circuit and if this input signal is some arbitrary sinusoid, like input signal, so if this input voltage, for example, let's call this Vt. Let's say if this input voltage, okay, if this input voltage is some arbitrary voltage signal, say V, say V and sine omega naught t. Okay, again, omega naught is the constant frequency of this particular signal. So we are applying sinusoids of different frequencies here. If that is the input here, so the output, okay, let's call that VR, voltage across the resistor. That is what we consider to be the output. That will have this magnitude multiplied with mod h, right? We saw that in our last class. So that will be this magnitude multiplied by mod h. What is mod h? This value. So into omega rc root over 1 plus omega square r square c square. Okay. And again, let me try pulling this. Okay, and the output is going to be a sinusoid, of course. Again, we proved this in our last class. The output is also going to be a sinusoid of the same frequency as in this one, except there will be an additional phase of this one. So plus pi by 2 minus tan inverse omega rc. So that's going to be the output signal in the steady state. So this is the steady state output. Again, we discussed what I mean by steady states. Okay, after enough time has elapsed, and again this signal has been there for a long time, so enough time has already elapsed here. So that's going to be the output. for this particular system. So understandably, this is quite simple, right? Again, so there is no issue with this, right? There is nothing difficult about it, right? So I'm applying sinusoids of different frequencies, and I'm seeing that the output is also sinusoid of that particular, also a sinusoid of that particular frequency, but the amplitude is different and the phase angle is also different. Let's just talk about the amplitude right now. Just talk about the amplitude for a moment. Okay, so let's see, let's say V equal to 1, because on the both sides I have V, right? So let's say the peak amplitude voltage here is 1. Let's say my input is this. Again, let's say input is sine 0.1 t, so 0.1 radian per second. Okay, so if I have that, question is, what is going to be the output? What is the voltage across the resistor? What is the amplitude of that? What is going to be the amplitude of that? What is going to be the amplitude of that? You just have to put, so you need to have the value of R and C. Say for that, for this particular example, again, let's consider R equal to, let's say for my convenience, R equal to 1, C equal to 1. Let's say that. Okay, 1 farad, 1 ohm, something like that. So if I have that, just put omega equal to 0.1, and subsequently you shall have omega equal to 0.1, R equal to 1, C equal to 1. Subsequently we shall have a value of that, right? All right. So with all of these, I can now say the amplitude of the output. What is the amplitude of the output? V into this, right? So this is the factor that gets multiplied with the amplitude of the input. So if this is the amplitude of the input, say if this is V equal to 1, what is going to be the amplitude of the output? 1 into this quantity. So if this quantity becomes big, then the amplitude of the output also becomes big. If this quantity becomes small, then the amplitude of the output also becomes small. So this is why this is called the amplitude response. Similarly, how much phase difference will there be with respect to the input to the output? That is given by this. So this quantity, as this quantity was amplitude response, this quantity is known as the phase response, right? So this is the amplitude response, this is the phase response, right? We understand that how the system changes the phase of the input, and this is how the system changes the amplitude of the input, right? Got it? Right? If the input has an amplitude of V, what is the amplitude of the output? That was my question. And again, today we are going to see how to check this programmatically, right? Without actually using our brain, but just by doing any computer programming. Again, this is what I really do. Practically, if I have some problem at hand that I cannot really solve analytically, or maybe I don't know the mathematics behind it to analyze things analytically, I employ computer programming. I just program that using a computer and try figuring out from there. Okay. So if I cannot solve a problem, I let the computer handle the problem. Okay. And for that, I need to write a computer program. Okay. So I don't have to assume particular values here, just for the moment. Or let's say assume some particular values here. R equal to 1, say C equal to 1. So say particular values here. So what is the amplitude response? Amplitude response was this quantity, which was this quantity, omega R C by root over 1 plus omega square R square C square. That is the quantity. And with this particular example where R is equal to 1, C is equal to 1, and again we shall see better examples than this. When R equal to 1, C equal to 1, this quantity becomes omega divided by root over 1 plus omega square. And now my objective is to figure out what this looks like. If I plot this, what this looks like. Okay, so we are calculating the amplitude response. We are plotting the amplitude response. Again, you might recall that this is just like plotting the Fourier transform of something, right? Because indeed this is the Fourier transform of something, right? H omega is the Fourier transform of something. And whose Fourier transform is this? This is the Fourier transform of the impulse response of the circuit, right? Right? So if the input was an impulse, this would have been the output. Okay. So this would have been the Fourier transform of the output. So that's the impulse response of the Fourier transform of the impulse response. Now let's start with a very small frequency, namely a frequency which is close to 0. If we have a 0 frequency, so what is the amplitude response? What is the amplitude response here? if I have a zero frequency, if I put omega equal to 0, what is the amplitude response? Of course, if I put omega equal to 0, the result is 0, right? Result is 0. So I can say when the frequency is 0 or rather very, very low, what is the amplitude response? 0. So this system does not let zero frequency pass, or in other sense, this system does not allow DC signals to pass to the output, right? Zero frequency signals means DC signals. This system will not allow DC signals to pass, and if the frequency is very low, like very close to 0, this amplitude gain would be nearly 0, right? So you can understand what is the amplitude of the output for this system. The amplitude of the output is determined by this scaling factor on the amplitude. So if the input voltage is, say for example 1, for example here peak voltage is 1, so that 1 volt gets multiplied with this quantity, and if this quantity is 0, then the voltage at the output, that's also going to be 0, right? So no voltage would appear across this. That's the idea here. Okay, so the output voltage would be somewhere here, so output voltage would be 0. Now if I keep on increasing the voltage here, okay, if I keep on increasing the voltage, what you will see that the quantity that's down below here, okay, so again try to understand what is happening here. So if omega is 0.1, then I have a 0.1 in the numerator, but in the denominator, okay, I have 0.1 whole square. So what is 0.1 whole square? It's 0.01. So in the denominator I have 1.01 and then a square root. That would be approximately equal to 1, right? And so on and so forth. So of course I can understand that omega is less than omega, so omega square is less than omega when omega is less than 1, right? So say when omega is 0.1, this is going to be 0.01. When omega is 0.2, this is going to be 0.002, 0.04, 0.04, and so on, right? So when omega is small, I mean less than 1, this value is going to be smaller. So this will have lesser effect on the entire thing. And as such, again, we shall do this programmatically, right? So don't worry if you don't understand how these things work. So this will roughly follow the value of omega, right? And now as omega increases and becomes greater than 1, what happens? If omega is, for example, 2, this is now equal to 4, right? Now when omega is greater than 1, omega square is larger than this. So gradually what will happen is, now as omega becomes very, very large, then what happens? Say for example omega becomes 10, then we have 10, then we have 1 plus 100 square, okay? So 1 plus 10 square, so 1 plus 100, so 101. What is the square root? So the square root of 101 is almost 100. So the square root of 101 is almost 10, right? So we have 10 here, and we have 1 plus 100 and the square root. So we have, so when omega is 10, I would have 10 divided by root over 1 plus 100. So that's 10, and the denominator is approximately 10 because that's square root of 101. So that approximately 1. So as omega increases, this value approximately reaches 1, right? So we would have a situation like that. Okay. So if I draw a smooth curve that joins these, okay, so what is this representative of? This is representative of the relative amplitude of the output with respect to the input, right? So this determines how much amplitude I have in the output with respect to the input. Again, just to tell you how I actually see this, so this is here. Say this is my frequency. Imagine this. Say this is, say, 2 radian per second. Say this is 2 radian per second, say for example, and say something like that. Okay, say this is 2 radian per second and this is the amplitude, say I don't know, some value, right? So if I put 2 here, that will be 2 by root 5, so that is going to be 2 by root 5. Okay, something like that. So that's the amplitude. So what does it mean? This plot tells me if I excite the system, so this was the system, right? So this is how we represent the system, right, with the box. Okay, this is the system. Okay, so this tells me that if the input is something like this, say 1 volt and then sine 2t, something like that, the output is going to be 1, the voltage of the output would be 1 into 2 by root 5 and then sine 2t and plus some phase angle, of course. This is what it tells me. So from this plot I can actually figure out what is going to be the amplitude of the output, because this is the amplitude response of the system, right? I think you got this, right? And as the frequency becomes very large, for example, if the frequency is, for example, 10, so for example, when the frequency is 10 radian per second, when the frequency becomes 10 radian per second, yes, this amplitude response becomes very close to 1, right? When omega is very close to 10, this is very close to 1, right? So if this input signal is, say for example, 1 sine 10t, okay, this is the input, the output is going to be very close to 1 into, so what is the output? That is approximately going to be 10 by 10 here. Okay, so as I said already, as I shown already, so the output's amplitude is approximately going to be 1, right, into sine 10t plus some angle phi. Okay, and that angle is determined by the phase response. Okay, so with that said, this particular system now does not allow low frequency signals to pass, or in other words, this system allows low frequencies to pass, or sinusoids of low frequencies to pass, but with a great reduction in amplitude, right? If I give it a low frequency input, what happens? It allows that signal to pass, but with a great reduction in amplitude, right? But if I give this system sinusoids of high frequencies as inputs, then this system will allow those signals to pass with minimal reduction in amplitude. Okay, and if I feed this system with sinusoids of high enough frequencies, then what will happen? This system will let them pass unaltered in terms of the amplitude, as far as the amplitudes are concerned. You get the point, right? So with that said, this system blocks low frequencies and allows high frequencies to pass, and as such this system is known as, so this system allows higher frequencies to pass and blocks lower frequencies, right? That is, the system is acting as a high pass filter. So this system acts as a high pass filter. So it allows high frequencies to pass and it blocks lower frequencies. Again, feel free to ask any question that you might have up to this point. So we had the same RC series circuit, but only difference is that we are measuring the voltage across a different element. Okay, previously we were measuring the voltage across the capacitor, and today we are measuring the voltage across the resistor, right? So depending on what element I am considering to be the output element here, so depending on what we are considering to be the output, okay, the same system can behave as different type of filters. The same system would have different frequency responses. So I applied arbitrary sinusoids here, and if I measure the voltage across this, I would only see the high frequency signals come out and low frequency signals being blocked. Okay, high frequency signals will come out of this and low frequency signals are going to be blocked out of this. But what we saw earlier in our last class that took place on Wednesday, we saw that if we measure the voltage across this, we would see that the system is behaving as a low pass filter. That is, all the low frequency signals are appearing to be here and the high frequency signals are being blocked. And that has to be true because of Kirchhoff's voltage law, right? So if I am looking across this, all the voltages across this, they are representative of the low frequency components. Where did the high frequency components go? Of course, the high frequency components ended up here across the resistor, right? Because Kirchhoff's voltage law will have to be satisfied, and accordingly, if I apply certain different frequency components here, a signal that has different frequency components, then from that particular signal that has different frequency components, then all the low frequency components will bundle up here and all the high frequency components will bundle up here, so that at the end of the day, if I add everything up, that equals to the input signal, right? Something like that. So different parts of the same circuit behaves like a different filter in that regard. Okay, because again, Kirchhoff's voltage law is entirely coming from the conservation of energy, conservation of charge, and those things, right? Again, this is just conservation of energy, right? So so like just like the previous class, if I only see low frequency signals here, then where did the high frequency signals go? Of course, the high frequency signals came here. And if I only see high frequency signals here, where did the low frequency signals go? Of course, they are here. Okay, so that's the idea. Again, feel free to ask any question that you might have at this point. Again, we are going to learn how to do this programmatically, because very soon we shall end up with examples which will be very hard for us to do without a computer. Okay, there's a question. One of you asking whether whatever is happening is independent of the amplitude of the resistor. No, it is entirely dependent on the amplitude of the resistor, and we shall see. Of course, try to figure out that if R has a different value than 1, then what happens? We would have a different quantity here, right? Then how quickly this changes or how slowly this changes will be determined by the value of the resistor. Okay, so the resistor has definitely some effect. Okay, and of course, from your very simple understanding of circuits, if this is a lower value resistor, then what happens? The capacitor gets charged or discharged quicker. Okay, the capacitor will be charging or discharging quickly. Okay, and if the resistance has a higher value, then the capacitor will be charging and discharging slowly, because of the time constant. Okay, right? So, and that will definitely have some effect in the final output here. Also, one point to note is that if R has a different value, then this is going to be different, right? If R and C, if any of these are different rather than just 1, okay, if this is, say for example 10, it is going to have a different value, right? It is going to have a different value, and accordingly what will happen, the changes that are happening here will be slightly shifted. Okay, the changes though, so the slopes will be different. Of course, if I have a 10 omega here and 100 omega square here, of course the slopes will be different, and if the slopes are different, things will happen slightly differently. Okay, this will still remain a high pass filter. Okay, this will still remain a high pass filter, this configuration, but what kind of high pass filter, that will differ, and what I mean by that I shall talk about shortly. Okay, we shall very quickly talk about that, later on we shall talk about that, so don't worry. But only thing is that how the system behaves with different frequencies, the nature will remain same, but the exact values will differ. So the idea is that the system will remain a low pass filter, the system will remain a high pass filter, and as such. But what are the amplitude response, exact value of the amplitude response, exact value of the phase responses, those will change. Okay, so those exact values will change, but the nature will remain the same. Okay. Yes, that's the idea, right? The slopes will be different, and accordingly, yeah, things will change accordingly. So don't worry about that. Okay, all right. So that's clear, right? So let's consider a series RL circuit. So I would do one part of the RL circuit and I shall let you do the other part by yourself. So let's consider an RL circuit, series RL circuit. And again, I am not going to do the, what should I say, the step response. You have to calculate the step response, which was an exercise earlier, right? Again, if you are somehow unable to do that after at the end of all these discussions, so then we shall try doing it, right? So I can put the resistance here and the so that's the idea. I can put the other element here. So basically have two elements, right? So what do I put where? So whoever tells me first gets me to choose that. I can put the inductor here, resistor here, or the other way around. Okay, we are talking about RL circuit. So what should I do? You tell me. Okay. Again, I have a voltage source here. So what should I do? You tell me, and you shall have to do the other one as a homework. Okay. And by the end of today's class, you shall have a computational tool with you. Okay, you shall learn a little bit of Python programming to deal with these particular situations. Again, as I said, after completion of the syllabus, we shall have a few classes on Python programming that will let you do all these things computationally, right? Okay. So this is my input. This is xt, and this is the voltage I'm measuring across this. This is output, considering to be yt. Where should I put what? Any choice would be good enough. Whoever tells me first. But just don't say two resistors or two inductors, right? That would be absurd. I think you got the question, right? Nobody typed anything. Do I put an inductor here? Do I put a resistor here? Okay, someone said inductor in the middle. What do you mean by middle? Here? Or here? Here, probably here, right? By middle you meant to say this, right? Okay. So the person who said inductor in the middle, please let me know if this is what you meant. Or if this is not what you meant, I will change the circuit. Okay. So that's your resistance, that's your inductance, right? All right. So I'm measuring the voltage across the inductor. Okay, right. So whoever came first got served first, right? Right, fantastic. So let's apply Fourier transform on this. Of course, the exercise will be just to reverse this and figure out what happens. Okay, if I measure the voltage across this, what will happen then? Just like we did. So apply Fourier transform on this. So if I apply Fourier transform on this entire circuit, of course, what happens? Everything gets replaced by their impedance. And just like we studied in our childhood classes on circuit theory and such. Okay, so that is going to remain R, and this is going to be j omega L. That's the impedance, rather inductive impedance, right? This is going to become x omega, and this is going to become y omega, right? So these things are understood. All right. So there is no confusion regarding this, I hope. All right. All right. So we are measuring the voltage across this. Very quickly, let's do that. Okay. So of course, what is the total current here? Let's consider the current to be I omega here, and we should be just IT here, right? All right. So I omega is the current through the circuit, and that's just total voltage across the circuit divided by this. So of course, and that's from Kirchhoff's voltage law, right? X omega divided by R plus J omega L. All right. So with that said, that's a very simple explanation. And of course, what is the voltage across the inductor? Okay, what is Y omega? Y omega. Of course, what is Y omega? Y omega is simply the voltage across the inductor. And there is one more thing. We don't always have to measure the voltage across the across something, right? The output does not necessarily have to be a voltage. The output could be a current. Okay. This frequency response does not only have to be a ratio between two voltages. It could be a ratio between a voltage and a current and a voltage, two currents, two voltages. It could be ratio between any two physical quantities that are related somehow. Okay, got it? So it could be the ratio of any two physical quantities inside a circuit or inside a system, right? The output could be anything, the input could be anything. All right, as long as they are related, we can find out a frequency response between them, right? So the input does not necessarily always have to be the voltage across something. It could be the current through something. Okay, and it depends on what we need. Okay, so you get the point. So with that said, the voltage across the inductor would just be the inductive impedance multiplied with the current. So J omega L into I omega, right? So J omega L into I omega, that's the inductive impedance, and that's multiplied with I omega. So what is I omega? That's X omega divided by R plus J omega L. All right. So that's it. If we simplify this slightly, okay, do I have to? No, let's see. So therefore, what is H omega? H omega here is again Y omega by X omega, and that gives me J omega L. And again, this entire discussion will be dependent on what we are considering to be the output. Because input is this input voltage, that is understood. What about the output? I could have considered the output to be the current here. And accordingly, I would have this to be the output. If I consider the current to be the output, then this would have been the output. Then this would have been 1 by R plus J omega L would have been the frequency response. Okay. So it's entirely dependent on what we are considering to be the output. All right. So I have here, I have R plus J omega L, and I think this is understood at this point, right? There shouldn't be any confusion regarding this. Let's do a slightly more useful simplification. Let's divide the numerator and the denominator with L. So rather, I would have J omega on top, and I would have R by L plus J omega here. And this has some uncanny similarity with the previous example, right? In the previous one, I had something like omega RC by this. This kind of has some uncanny similarity with the previous one, right? So if I ask you, then find that is the frequency response. So okay, this is the ratio of the Fourier transform of the output to that of the input. What is the input? Input is the total voltage across the circuit. What is the output? Output is the voltage across the inductor here, right? So with that said, what is the amplitude response? That is going to be the amplitude of this quantity. And if I take the amplitude of this quantity, which is J omega divided by R by L plus J omega. So subsequently I would have a omega here. Again, I'm considering positive frequencies only. That's why. And root over, I would have R by L whole square plus omega square. All right. So that's the quantity. And what about the phase and what about the phase response? Phase response is again going to be the phase of this numerator minus the phase of this. Okay. So phase of J omega L minus phase of phase of J omega by phase of R by L plus J omega. Now what is the phase of J omega? Again, it's a complex number, purely imaginary number with a positive real part. So angle is plus pi by 2, and this is minus tan inverse. It's a complex number on the first quadrant. So tan inverse omega by R plus L. Tan inverse omega, so R by omega by R by L. Okay. tan inverse imaginary part by real part. So this is going to be pi by 2 minus tan inverse omega L by R, right? So that's going to be the phase angle. So again, so if I consider, if I just pull this back here, copy and paste this. So what I right now have figured out is that if this is a sinusoid, some arbitrary sinusoid, okay, that looks like this, say this is voltage, okay. If this is some arbitrary sinusoid, which is V sine omega naught t, okay, it could be cosine, it could be anything. It could have some initial phases here. The output, which is voltage across the inductor here, that's going to be V. Then this amplitude response, where is it? Yeah, this one, into omega by root over R by L whole square plus omega square, because that was it, into sine, okay, and let me shrink this figure here, into sine, and omega naught t, the frequency won't change, only the phase angle will change, and the additional phase would be plus pi by 2 minus tan inverse omega L by R, right? So that is again being represented as this. And again, just like the previous one, this is going to be a high pass filter. I believe you understand this, right? By now, you probably understand that this is going to be a high pass filter, right? This is indeed going to be a high pass filter. All right. So say example would be R equal to 1 and L equal to 1. Of course, we would then have mod H omega, which is this quantity, that's going to be 1 by root over 1 plus omega square, sorry, omega by root over 1 plus omega square, and this is exactly identical to this, right? All right, this is exactly identical to this. So this is exactly going to be a high pass filter, just like before. So okay, this is very similar high pass filter. In short, I write HPF, high pass filter, like the previous example. So I can have a series RL circuit and measure the voltage across the inductor. That gives me a high pass filter. So if I tap the voltage from this gives me a high pass filter. All right. So here in this scenario, all the low frequencies will bundle up across the resistor, and the high frequencies will bundle up across the inductor. So if I measure the voltage across this behaves like a high pass filter. But similarly, if I take a RC series circuit and measure the voltage across the resistor, then it acts as a high pass filter. Of course, from your common knowledge, you can say if I measure the voltage across this will act as a low pass filter, but that will be your homework. Okay, your homework will be to look at this. Okay, consider the output to be across this and measure it, right? That gives you that low pass configuration for this circuit. Now, for the moment, I have two circuits. Now we have a question, right? So I am drawing two circuits that have the same frequency response, identical frequency response, right? Both of them are acting as a high pass filter, right? So let's go back. So let's draw this. So I have this configuration where I have a capacitor here, and a resistor here. If this is the input and this is the output, and this is 1 farad, this is 1 ohm, just say, okay, then this has a frequency response which is y omega by x omega. Hold on. these are the frequency response, which is y omega by x omega for this particular values. And look very carefully, I would just have these as the frequency response. So r equal to 1, this is equal to 1, so I would have j omega by 1 plus j omega. Okay, so this acts as a high pass filter, so it's a high pass filter. And similarly, just like the example I saw few moments ago, if I have hold on, so this is x omega, here this is y omega, and this is 1 Henry for example, and this is 1 ohm. Okay, then again your h omega would be y omega by x omega. This is equal to, again, what is h omega? J omega by this, just like this one, it was this. So here r equal to 1, c equal to 1, so both of them are 1. So similarly, this is going to be j omega by 1 plus j omega. So these would have the same frequency response behavior, and as such they will have the same impulse response, of course, because if we take the inverse Fourier transform on the frequency response, we get the impulse response. So they behave identically. You got the point, right? These circuits would behave identically from the perspective of the input signal and the output signal, because they have the same impulse response. And I said, if I am dealing with a linear time invariant system, the impulse response is entirely responsible for the behavior of the system. We can figure out everything we can figure out about the system by just looking at the impulse response of the system. By just looking at the impulse response of the system, we're actually able to figure out everything. Because if I have the impulse response, I can convolute that with any arbitrary signal to calculate the output. Okay. If we have the impulse response, we can take the Fourier transform of that and we get the frequency response, just we have got that. Okay. So we can understand all the behavior of the system by having the impulse response of the system. And here we are having two different circuits entirely, which have the same impulse response because they have the same frequency response. So they have the same impulse response. So these circuits will be identical in nature from the perspective of an input signal and an output signal. All right. But my question to you people as electrical engineers, is there any subtle difference between these two circuits? Because as far as our mathematical understanding goes, these two circuits will behave identically to any input signal. From the perspective of an input output, okay, these two systems are identical in nature because they have the same frequency response and they have accordingly the same impulse response. So if I give it some arbitrary input here, whatever the output comes out of this circuit will be identical if I put that same arbitrary input here, and the output will be identical because these two circuits have the same impulse response, same frequency response, and same everything, right? But the internals are not the same. But my question to you now is there any difference between these two circuits apart from the mathematical perspective? As far as the mathematics of signal processing goes, these two circuits are identical. But from an electrical engineering perspective, is there any difference? So if you think there are some differences, try to figure those out, because the behaviors of this circuit will be identical, both in terms of frequency and in terms of time domain responses, everything, because they have the same impulse response, same frequency response. But is there any subtle difference between them, between these? No, both of them are voltage outputs. Someone is saying one of them is a current output. No, 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 no. Both of them are voltage output. We are measuring the voltage across the inductor. We were measuring the voltage across the inductor, right? Yeah. Y omega was voltage across the inductor, right? Y omega was voltage across the inductor. It wasn't current. Y omega was the voltage across the inductor. That is what it is. I omega was current, but Y omega was current through the inductor, impedance of the inductor multiplied. So it was voltage across the inductor. So both of them are voltage, not current. Both of these quantities are voltages. And again, we are drawing them as two-port parameter networks. If this is how I draw it, it means that both of them are voltages, right? So this is a voltage, this is a voltage. This is also a voltage, this is also a voltage. Everything is a voltage. I said I could take current, but that would give me some other results, right? But the idea is we are now considering the input to be a voltage, output to be a voltage in both the scenarios. So as far as the current voltage scenarios go, they are identical in nature. So now question is, I mean, is there any special thing? Is there any special difference between these two circuits? Are they identical in nature? Yes, from a perspective of signal processing, they are identical in nature because we are considering everything to be ideal. That's the important thing here. Whenever I am drawing a capacitor, I am thinking it's an ideal capacitor. Whenever I am drawing a resistor, it's an ideal resistor. Whenever I am drawing an inductor, it's ideal inductor, right? But nothing in real life is ideal, right? But in inductor, you would probably have something called, so if we have an inductor with high enough inductance and all, right? You probably don't have air core, you have some ferromagnetic core, right? Inductor is nothing but a coil wrapped around some ferromagnetic material, right? The ferromagnetic material don't have a linear BH curve, right? So what happens, the flux density does not linearly increase with, so basically with an inductor, the flux density will not always linearly increase with the magnetic field intensity, right? So you might increase the current through the inductor, but the flux density will not always be proportional. So for this inductor, try to understand what happens. The very basic configuration for an inductor. So for example, I had an inductor, I had drawn it earlier, right? And I'm exciting this with any supply here. So I said, of course, for an inductor, you know, V equal to LTI dt, right? But where does that come from? This comes from the very simple fact that L, we consider that d phi is proportional to di. Okay, or rather I would say I is proportional to phi, right? For an inductor, we are assuming something like this. We are assuming that the rate of change of current would be proportional to the rate of change of magnetic flux, right? Rate of change of magnetic flux. And you people have already seen something like this. We have BH curve for these things, these inductors and all. So for the ferromagnetic materials, if you have a ferromagnetic core, okay. So what happens? The H is proportional to current. That's understood, right? H has a unit of ampere turns, right? Magnetic field intensity, H has a unit of ampere turns. So if you have n number of turns, and if you put I ampere of current, then H is basically number of turns into the current. So H has a unit of ampere turns, okay? And B has a unit of Tesla, okay? That's Weber per meter square, right? And phi has a unit of Weber, okay? So yes, so B is proportional to phi here. So for a BH curve, I can also write this as phi I curve. So if this could be a BH curve, this could also be a phi I curve, right? Because B is directly proportional to phi. Okay, because B is just phi divided by area. Okay, and H is nothing but number of turns into total amount of current. So ampere turns. So yes, so I can write that. So for a BH, instead of a BH curve, I can write phi I curve. But the idea is, for a ferromagnetic material, for an inductor, if I have an inductor which is a coil wrapped around a ferromagnetic material. So if this was an inductor without any ferromagnetic material core, okay, with for example air core inductor which has very low inductance, but then the characteristic would have been linear. Okay, for air or vacuum, for example, okay, the phi I, this relationship between phi and I is linear. But for a ferromagnetic material, what happens if I have a ferromagnetic core with an inductor? What happens? This curve automatically goes into something called saturation. So I might see a linear zone. Again, you studied this in other subjects, right? I might see a linear zone up to a certain point of current, up to a certain value of H. But if I go on increasing the current up beyond a certain limit, what happens? All the magnetic dipoles inside the ferromagnetic material would have already aligned, right? So the increasing current will not have a proportional increasing effect in the flux. So this is magnetic flux. So increasing current will not have a proportional increasing effect in the magnetic flux or magnetic flux density per se. So the inductor will no longer remain linear beyond a certain value of current. And as such, inductors are not linear up to beyond a certain point. But capacitors are far more linear than inductors. Okay, inductors. Do you get the point? The point is that here we are considering everything to be ideal. Here we are considering that this capacitor, this inductor, these resistors, they are carrying their linear time invariant characteristics throughout every scenario. But in real life, that never happens. In real life, nothing is ideal, nothing is linear, nothing is time invariant properly. So everything has something to do with something, right? So nothing is linear so everything is linear up to a certain point. Okay, so we can linearize things. We can simplify and understand, okay, I can consider this to be linear. But in reality, things become non-linear very quickly, very easily, right? All right. And also, if I increase the frequency, then again, the behavior of an inductor degrades very quickly. That also happens with capacitors. Okay, if I increase the frequency of a capacitor, then what happens? All the internal resistance in the material of the capacitor, they come into effect. And subsequently, with higher frequencies, the capacitors start acting like a resistor. Then with even higher frequencies, capacitors start acting like inductors. Mind-boggling, right? The capacitors we are considering to be capacitors, with high enough frequency, they act like resistors. Then even higher enough frequencies, capacitors themselves become like inductors. So there are so many things that happen inside this, and we just simplify everything. Okay, simplify everything. Okay, that is how the engineering goes here. We simplify everything up to the point that it does not break anything. The moment that our simplification starts breaking our scenario, starts breaking our devices, we then figure out what happened by removing the simplifications. So in engineering, we always start with simplified assumptions. We simplify everything up to the point where things really work, okay, more or less. But the moment things start breaking because of our simplifications, so we then try to take out one simplification after another, and up to the point where we have less amount of simplifications, but the things are working again. Okay. So in many scenarios, we do have to consider the other scenarios, that inductors are not ideal, capacitors are not ideal, even resistors are not ideal, right? So there are so many things that actually happen in real life that we do not consider for the most part, okay, unless we have to consider them. That's the behavioral difference here, right? So you have to understand that difference here. So theoretically these two are identical, but practically they are very, very different. Okay, their nature is very different. So I believe I got that out of the way. So again, so with that said, let's jump into a series RLC circuit. Again, if you have any query, feel free to ask. Let's consider an RLC circuit, and I won't ask you where to put what, because now in this example I shall be considering current to be the output. You will see why. You shall soon see why. Okay, I'll consider current to be the output here. Simple RLC circuit, because that is how we've studied a simple RLC circuit. Again, feel free to ask any question that you might have already. Okay. That's any signal input here. That's R. That's L. That's capacitance. I could consider the voltage across the capacitor to be the output. I could consider the voltage across the inductor to be the output. I could consider the voltage across the resistor to be the output. I could consider anything to be the output. That would entirely be up to me. Okay, but the point is I'm now considering the current through everything to be the output. So this is the current through everything, right? I'm considering that to be the output. All right. So and again, this is the input. All right. So this is R, this is L, this is C. Again, if you have any query up to this point, feel free to ask. I can always go back and answer your questions. All right, so let's apply Fourier transform the circuit, and I'm considering the current to be simply YT. Here my current is the output. Again, you could consider anything to be the output, because I want to prove a point here, and that is why I'm putting the current to be the output. Again, you can have anything. All right, so let's copy paste this again. Now, of course, I have applied Fourier transform with this, and as such, this is what is going to be. So as such, I shall have X omega here. The current through this would be Y omega. Current through everything, because it's a series circuit after all. And the impedance here will be R. The impedance here would be J omega L. And impedance here would be 1 by J omega C. So that is understood, right? So that's the that's after Fourier transform here, right? So again, what is the current? I am writing current equal to Y omega, which is equal to total voltage divided by total impedance. That's again Kirchhoff's voltage law, right? So I have X omega divided by R plus J omega L plus 1 by J omega C. All right. So you have seen this kind of things in your basic electrical engineering or maybe circuit theory classes, right? So you have seen something like this. That is why I'm writing it this way. Okay. So if I do the multiplication here and do the simplification here, so I would have H omega. So what is H omega again? H omega is Y omega by X omega. So I would have 1 by R plus J omega L plus 1 by J omega C. And if I multiply the numerator and the denominator with J omega C, I would have J omega C divided by J omega RC plus J square omega square LC. So I'm adding J square omega square LC plus 1. Now there is a reason why I'm writing J square omega square LC, not just minus omega square LC. Okay, I could have written minus omega square LC, but I'm not writing that because soon it will be clear why. Okay, I could have written minus. No one could have stopped me from doing that. Okay, so I would have j omega c, and I have j square omega square LC plus j omega RC plus 1. So that's now the frequency response of the circuit. When I'm considering the output to be the current through the entire circuit and the input to be voltage across the entire circuit. That is fine, right? You people already know these things by heart, right? So I believe. All right. So there is no issue with this. Now let's consider a very simple example. Okay. Let's say with this, let's calculate the total impedance here. Let's calculate the total impedance. Now the moment I want to calculate the total impedance or something like sorry, not total impedance, let's calculate the amplitude response. So I have to take a mod there, and if I want to take a mod there, of course I have to put j square equal to -1 and do the calculation accordingly, and such and such. Okay, but I'm not going to do that here for this moment, but let's try something else. So if I write something like this, I would have mod of j omega c by j square omega square LC plus j omega RC plus 1. All right. So let's divide everything by LC for a moment. Okay, here let's do that here. Let's divide everything by LC, for example. So if I do that, divide everything by LC, what do I see? Divide everything by LC. So I would have j omega into 1 by L. So I would have j square omega square. Dividing this by LC would give me j omega R by L plus 1 by LC, right? So instead of this, I would rather have j omega into 1 by L divided by j square omega square plus j omega R by L plus 1 by LC, something like that, right? All right. Now I could have taken care of this j square and written it up with a minus sign, right? But I haven't done that because there is a reason for that. And again, for my convenience, let's write this as LC, multiply everything with C. That also does the job. There is no confusion whatsoever, right? There shouldn't be any confusion regarding this. All right. Now the point is that if we wrote, okay, try to understand what I mean here. Okay, as far as the amplitude goes, there wouldn't be any problem. Okay, so I could, again, let me just simplify this here. I'm writing a C here and I'm writing LC here, no problem, right? So as far as the amplitude response goes, I could write -1 here. So let's write down. So I would have j omega into 1 by LC. I could have written -1 here. So instead of j square, I have -1. So I would have minus omega square plus j omega R by L plus 1 by LC. Okay, and that would have been C mod. On top I would have j omega 1 by LC, and here if I combine the real parts, I would have 1 by LC minus omega square, and imaginary part is j omega R by L. Okay, and that gives me C into, on top I would have j omega L by C. So that is going to be omega L by C. That's going to be let's keep this C here. This is going to be omega into 1 by LC, and now here root over here I have square root, this one square, of course that's the real part, 1 by LC minus omega square plus omega R by L square, right? nothing has really differed, right, by putting a minus sign here, right? But now, why I was hesitant about putting a minus sign, skipping that omega square, j square will be evident. So that's the amplitude response. And again, we are not going to dare drawing this without a computer here. Okay, there are many reasons for that. You shall see why. Okay, because this is already in very complicated territory here. Okay. All right, and what about the phase response? What about the phase response? That's the amplitude response. What about the phase response? The phase response would be the phase of this entire thing, rather this entire thing, right? So let's copy this. The phase response is the phase of this entire thing, right? Again, try to follow, okay, because again, this C is a constant, positive constant, go outside, it is irrespective of independent of everything. So I'm talking about the phase of j omega 1 by LC minus phase of j square omega square plus j omega r by L plus 1 by LC, right? So of course, the phase of this already we have established. We have been establishing this for a very long time already. So the phase of this is pi by 2. Okay, the phase of this is pi by 2. Okay, minus we have this, the phase of j square omega square plus j omega r by L plus 1 by LC. We have the phase of this. Now let me ask you this simple question. Now let's try to figure out what I mean here. Okay, let's see this. Okay, now from the argument, now let's go back, recap from our school level mathematics, right? Recap. So recall rather that if I have two complex numbers, say z1 and z2, and if I want to find out the argument of that, so that is the angle of this entire thing. Okay, so I used to write, when in school you used to write arc, right? Nowadays we write just an angle. So instead of arc, we write an angle, right? Something like that. Of course, understandably, that if I have this, every number, every complex number has that polar representation here. That polar representation, what was the polar representation? This is mod z1 e to the power j angle z1, right? And this is mod z2 e to the power j angle z2, right? That's the argument of that particular complex number. So with that said, this is angle. So now these are just real number getting multiplied. So I have mod z1 mod z2 getting multiplied together, and I would have e to the power j angle z1 plus j angle z2. Now out of these, I can write that I have mod z1 mod z2 and e to the power j angle z1 plus angle z2, right? All right. So this again does not affect the, since this is a positive quantity, would not affect the angle. So what is the angle? Angle would be angle of z1 plus angle of z2. So if I have two complex numbers multiplied, and if I want to take the angle of that, if I want to figure out the angle or argument of that, then the argument of that would be the individual sum of the arguments. But again, there is plus n pi here. Okay, and there is a reason for that, but we are skipping that. We are skipping that for this particular scenario. Okay, there is plus n pi, just to keep the angle between inside the principal argument range of tan inverse. Okay, tan inverse has the principal argument range between certain values, and accordingly there are restrictions to follow. Okay, but in any case, you can understand that this is the plus. So for example, this is the thing we are interested about, right? Got it? All right. So now let's think about this. Okay. And with that, with this, let me just give you a very simple idea here. Okay, I'm asking you to calculate the angle of this complex number, j omega plus 1. What is the angle of this complex number? Please say. What is the j omega? What is the angle for j omega plus 1? Something like this. What is the angle of that? Of course, this is just a complex number. Say, I'm saying complex. Say 1 plus j omega. What is the angle of that? That's going to be tan inverse omega by 1, right? So tan inverse omega, something like that. Got it? Got it? So when omega is very small, then what is the angle of this 1 plus j omega? When omega is very small, what is the angle of this? When omega is very small, what is the angle of this? That's 0, because tan inverse 0 is 0. But when omega is very large, very high frequency, for example, what is the angle of this? That's going to be tan inverse infinity. But what is tan inverse infinity? Tan inverse infinity is pi by 2. Tan inverse infinity is pi by 2, right? Right? Tan inverse infinity is pi by 2. Alright? Got it? Very good. Now, with that said, if I now ask you this, yeah, tan inverse omega. So now if I now ask you this, I have two complex numbers multiplied, 1 plus j omega, 1 plus 2j omega. So say for example 2 plus j omega, say. Okay? Okay? If I say something like that, then of course you know that I have to do something like this, 1 plus j omega, in order to calculate the total phase angle. 2 plus j omega, you have to do something like that. Individual phase angles, add them up. Now what about, so of course this is going to be tan inverse omega plus tan inverse omega by 2. Understandable? Quite simple, right? This is tan inverse omega plus tan inverse omega by 2, right? So imagine that by you. Now if I say, then question is, what about low frequencies? When frequency is very low, when frequency is very low, then what is the phase angle of this entire thing? What is the phase angle of this entire thing? Of course, the phase angle of this entire thing is tan inverse 0 plus tan inverse 0. So that also goes to 0. Got it? And if I say when omega is going to infinity, then what is the phase angle of this entire thing? Once again, that's tan inverse infinity plus tan inverse infinity. That's going to be pi by 2 plus pi by 2, right? Yeah, tan inverse omega plus tan inverse omega by 2. So, and now when omega goes to infinity, then what happens? What is the phase angle? Tan inverse pi by 2 plus tan inverse pi by 2. So both of them are contributing certain phase angles, right? Right? So I would have pi by 2 plus pi by 2, which is equal to pi. So pi is the total phase angle, right? Got it? All right. All right. So we calculated the phase angle of this entire thing. So that's so when for low frequencies and high frequencies. Now, so we have been dealing with this, right? We have been calculating the phase angle of this, right? Right. So with this, I could have also multiplied these two complex numbers, right? I could happily multiply these two complex numbers. And I could say 2 plus j omega plus 2j omega plus j square omega square, right? Now, with that answer, now I could simplify this further. I could have written 2 plus j omega plus 2j omega, that gives me 3j omega. And then I have j square omega square, so that becomes, j square is minus 1, so minus omega square. Now this is angle 2 minus omega square plus 3j omega. Now this kind of is behaving like a simple complex number, right? Right? So a single complex number. So this is going to be tan inverse 3 omega by 2 minus omega square. Now unfortunately we have a problem now. because this cannot go beyond a pi by 2, right? So this cannot go beyond pi by 2. You get the point, right? So tan inverse anything is limited between minus pi by 2 and plus pi by 2, right? So this cannot go beyond pi by 2. So whatever value of omega I put here, the phase angle cannot become greater than pi by 2. But we moments ago saw that the phase angle, when frequency is infinite, the phase angle actually should be pi, not pi by 2, but pi. But here, since I got rid of that j square by writing -1, I have a problem in figuring out the actual phase of the system. You get the point, right? That is why we do not do not go in a hurry and replace all the j square in by -1. We do not do that, because if I do that, then the phase angle, the information of the phase angle will be kind of lost. Okay. But the information on the magnitude will not be lost, because at the end of the day, we just consider j square equal to -1 anyway. Okay, so nothing will change in as far as the magnitude is concerned, but for the phases, things will drastically change. Things will drastically change, and we would have very drastic effects on that. With that said, now let's use a little bit of Python programming to see how we can implement this using very little set of code, okay, and figure out what happens with systems when I excite the systems with these signals and any signal, for example, right? So again, gradually we shall move into a Python programming in full-fledged Python programming. Gradually we shall move into that, and as such, let's start with that. And again, if you have any query, feel free to ask. Okay. Because in order to calculate the phase angle of this, we shall have to do an entire we shall have to do some multiplication here, so that we can represent this as a product of two complex numbers. Then we shall be able to actually find out the phase angle in using exact values, right? So if you have any query, feel free to ask at this point. Okay, so someone is asking, why is this happening? Why is one of the phase angles are getting eliminated? It is simply getting eliminated because here, try to understand, I am putting j square equal to -1. So this is being treated as just a single complex number, right? Not a product of two complex numbers. So the phase contribution of another part of that is somehow getting lost. Okay, the phase contribution of another part of that is somehow getting lost here. So that's the important point to note here. Okay, here same thing will happen if I write j square here. So this is a product of two complex numbers, right? But if I write j square equal to -1, this could be treated as just like a single complex number, right? So that's not ideal here. Okay, and again, while doing the programming, we shall write j square as j square. Okay, we shall let the computer program decide what to do with that. Okay, and it will decide correctly for us. Okay, again, we could write j square equal to -1, but in that case we shall have to do a lot of mathematical shenanigans to actually get the correct answer. Okay, so let's see how the systems behave with different frequencies, right? So let's jump into Python programming now, and let's see how we can actually do that. So again, I shall not be using my installed Python software, whatever. Okay, I shall be using Google Colab, so everyone can follow properly. Okay, so now, so let's go to colab.research.google.com. So colab.research.google.com. So this is the website where you can do Python programming. Okay, and everything will be saved as like Google Doc. Okay, and everything will be saved in your Google Drive. Okay, and let's go to this and do these frequency response calculations. Using Python. Okay, right? Because our engineering landscape is changing rapidly, right? Instead of teaching everything theoretically, you should learn how to use your computer to actually calculate everything, right? Because we do not really use our brains like anymore to compute things. We use our computers to compute things, and we figure out how to tell the computer to compute the things, right? We do not always rely on our brain for doing computations, right? Because our brains are designed to do thinking, okay, do analytic thinking, okay, and computers are good at doing computation. They are very poor at doing analytical thinking, right? So if it is about analytical thinking, use your brain. If it is about computation, some sort of computation, use your computer. Because as far as computations go, your brain can make a mistake, but computers won't. Okay. Again, right? So let's go into that. So I shall jump to my screen here, okay, and say I shall go to collab.research.google.com. All right. So I have gone to collab.research.google.com, and if you are opening this for the first time ever, okay, you shall see quite a few things, and it might ask you to add Collab as an app in Google Drive and as such. These things happened. Okay, you just agree to whatever Google says, right? So why do I promote this environment? Because simply because you get to have a very good computer given to you by Google to do all your Python based computations, and everything that you write gets saved as a Google Doc. Just like a Google Doc, you can share the file with anybody. Okay, you can collaborate with people, and even if you don't have a very good computer, okay, this Google Colab platform takes care of that, right? You have a computer with a GPU, so even if you're doing some things like machine learning and as such, so I have been doing machine learning here, so there are so many things, so you can do that, okay, on this online environment. Okay, all right, so that's, so it might show you some few things. So for example, it might show you how to get started and such. Okay, this is again something called a Jupyter notebook environment for Python programming. Python programming, you can do Python programming with many different ways. This is one of the ways, because this is kind of a very useful way for scientists and engineers, because here all the results and everything gets saved like a like in a web page like format. Okay, with that said, let's create a new notebook. Go to file and create a new notebook, and at the end of the class I shall share this notebook with you, but I shall still encourage you to follow along with this. If you can follow along with me, then it becomes actually a really good thing. Okay, so just like a Google Doc file, as you can see, let me just zoom in. Just like a Google Doc file, as you can see, there is a Google Drive icon here. So everything is getting saved in Google Drive. So I'm saying signals class, and the date for today is 2020 05 and 15. Okay, so I'm saving that file like that. Okay, the file name extension is .ipynb. Actually, this is a project that started as something called IPython notebook. Okay, so IPython notebook, you can understand why it is called that. Anyway, so I shall teach you the bare minimum, okay, to go along with this, because again, this is like you're going to a war, okay, and while going to a war, you don't have much time to learn everything from scratch, right? Okay, so you're going to a war, so you got a training for like 5 days, for example, okay, and now you have a machine gun and you are going to a war to save your country, for example, right? Something like that. This kind of things do happen really. Okay, so this is like that very powerful weapon here. So Python is like a very powerful weapon, and you can have this for free. You are not violating anyone's license, right? If you install a pirated software, you are violating someone else's license, right? Here you get it for free of cost, and free as in freedom. You can do whatever you want. And people like Google, Google and Microsoft also has a platform like that. They are giving you virtual machines for free so that you can do Python programming, okay, and do all of your computations for free online. Okay, that is a good question. Someone is asking, do you do control systems require Python? Historically, no. Okay, historically, control systems did not require Python, right? But when I did my master's degree, I did everything. Again, I did my master's degree in control system. Okay, and when I did that, I did everything using Python. Okay, I did everything using Python, and nowadays you can do everything using Python. So everything that you can do in your control system engineering, you can do with your Python. Okay, so historically people used to use MATLAB for that. Okay, MATLAB and Scilab for that. But today, whatever those softwares can do, Python can do, along with many other things. I mean, along with millions of other things that MATLAB and Scilab won't be able to do, Python can do, right? So in a sense, if you learn Python, you have learned a tool that can deal with anything, not just control systems, but anything. Okay. And I have a video on my YouTube channel that shows you how you can do control system engineering with Python. But that assumes that you already have studied a paper on control systems. Okay. With that, and that also assumes that you already know a little bit of Python. Okay, with that, I have a very small video, like a 2 or 3 minute video, depicting everything that you can do, rather a very small set of everything that you can do using Python. I have that on my channel. Okay, so you can watch that if you wish. Okay, so with that said, again, Python can be used for signal processing, data processing, designing websites, designing applications like mobile applications and desktop applications. Okay, doing data science, and for doing AI and machine learning related programming, Python is the #1 choice. And yeah, you can understand from like literally whatever you can think of doing programmatically, you can do using Python. And Python is a very easy programming language to learn. Okay, so the language barrier, okay, I mean, is not much. Okay, got that right? Language barrier is not much. But again, today we are going to start from a kind of we shall jump start our discussion here, right? We shall have a abrupt jump here, right? I shall not be teaching you the basics of Python, but we shall have a jump. But the very basic of Python you should learn is that you can use Python as a very powerful calculator, for example. So for example, I can say computations like this: 1 plus 2 plus 3 plus 2.4, something 2.5, something like that. And if you run this cell by clicking on this, the first run would take some time because it is now initializing the virtual machine. That would take some time, and the rest of the calculations would be simple. So yeah, we are using Python as a very simple programming, what should I say, computational environment, right? So we can do that. Okay, but this is not it. Okay, this is not it. Python is a very powerful programming language in a sense that you can do things very easily here that you will be hard pressed to do in other programming languages. For example, so this is how you raise something to a power, say 2 to the power 8, for example. This is how I add 2 to the power 8. Double star is power, right? Star is multiplication, you understand that. Okay, division is a slash, and this is power, for example. That's 256, right? Very simple. Now, what if I have a power like this? So for example, something like that. It's a huge number multiplied, raised to a huge power. This is 122 raised to a power of 1, 2, 3, 4. This is going to be a very large number. And if I run this, Python has no trouble figuring out the number. As you can see, this is a very long number. As you can see, this slider is so, like, you can see, this is a very long number, right? And Python got this anyway. I mean, doing this using C or some other programming languages would be difficult, but it's possible. It's difficult, right? Probably you won't be able to do it, right? So it has very powerful capabilities, right? And so let's jump into what I wanted to say here. Okay, so let's delete all these cells. Okay, let's delete those. How do I delete cells here? Unfortunately, somehow I do not use this. Okay, in any case, let's forget about that. How do I delete cells? View, edit, delete selected cells. Delete selected cells. Right. So what I'm going to do, I am going to jump into some Python computational environment known as the Pylab environment. So just note that. So I'm writing %pylab inline. So and running this. So if you run this, so it says something like populating interactive namespace from NumPy and Matplotlib, and we shall have proper classes on Python that teaches you what I mean by this. Okay. So with that said, now let's define our frequency response function, right? So how do you define functions in Python? Very simple. You say def. So h is going to be a function here. And again, I think you can see this. Let me just zoom in a bit. Okay, h is a function. Of course, h is a function of omega, right? H is the function of omega, right? Got it? H is a function of omega. So understandably. So, but h is also a function of r, l, and so let's do that RC circuit first. Okay. H is also a function of R and C. If I consider R to be parameters, R can change, of course. With that, H is a function of R and also the value of capacitance here, right? Like that. So this is how you define a function. Okay. You write def and name of the function is H here. It could be anything, right? It could be anything. This could be a name of the function, right? I'm just writing H. So H is the name of the function here. So you put colon and then you put an enter. Now look very carefully, we have a tab here, right? You have a small tab here. So that, and this is very important. In Python, what is inside your code block or what is in the range of this particular code block, okay, is determined by the tab. In Python, you don't have excessive curly braces. In C programming, yeah, if you define a function, you have to put curly braces and write everything inside curly braces, right? In Python, you don't have to do things like that. All you can do, you can put tab here. Okay, you can put enter and that tab is automatically given for you. And that tab determines the scope of whatever you are writing, right? So in C programming, this scope is determined by whatever is written within the curly braces. So in C programming, if whatever I write within the curly braces will determine the scope, right? So what I mean, everything I write inside those curly braces in C programming language will be inside this function. But here, everything is determined by this tab. Okay, I hit a tab and whatever I'm going to write right now within that will be entirely determined by this. It will be entirely done through this. Let's write a code. And there's one more thing. In Python, dealing with complex numbers is pretty easy, right? So I can say in Python, so for example, I can say 1 plus 2j. That gives me a complex number. Okay, that gives me a complex number. What is 1 plus 2j? That's my complex number. Okay, right? So I can say 1 plus 2j and I can raise it to a power. So this is 1 plus 2j whole square. This is 1 plus 2j whole square, right? Like that. Say 3 plus 3 minus, say for example 5j, and let's raise this to a power of 0.5. So we're taking a square root of a complex number. We can do that. So you can understand that using Python we can deal with complex numbers pretty easily, right? So let's pull this here. Okay, so with that said, let's deal with what I want to do with. So h is a function of omega. I'm writing w. You have to understand it's omega. So it's also parametrically related to R and C. So I'm writing something like that. I'm putting a colon and inside this indented block, okay, I'm writing whatever I want to write here. Now here, this is a function, right? H omega is a function. And what does the function return? The function returns the value of the function. So in Python and in C programming language and in many other programming languages, we return the value of a function. So this function takes omega, R and C as arguments and it returns the value of the function, right? Now let's consider the low pass filter scenario. For the low pass filter scenario, so what was the value? What was the for the low pass filter? What was the for the low pass filter scenario? What was the impedance? What was the frequency response? I think that was 1 divided by 1 plus j omega RC. But what is j? J is 1j omega RC, right? So 1 divided by 1 plus j omega RC. So in Python now we have defined the particular frequency response function. This is 1 by 1 plus j. Now instead of j, just I have to write 1j, right? Because j is 1j. 1j omega RC. That was the frequency response function, right? I think you got this, right? But at this point you are done. You have defined the function, frequency response function. Okay, you have defined the frequency response function. Okay, it's so easy actually in Python, right? Now once you have defined the frequency response function, now what do you want to do? You probably want to plot the amplitude response. You probably want to plot the amplitude response, right? You probably want to plot the amplitude response, right? So let's see how we can plot the amplitude response. But again, try to understand, in order to plot the amplitude response, you need to have a range of frequencies for which you want to plot it, right? Maybe you want to plot the plot this from 0 frequency to, say for example, a frequency value of, say for example, 5 radian per second, something like that, right? So you want to plot from a frequency value of 0 to a 5, right? So in order to do that computationally, what you have to do? You have to allow the computer, or allow the Python program to allow Python to compute this value for different values of omega, right? You have to allow Python to compute this for different values of omega, right? You have to change omega from 0, then next value will be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and so on, something like that, right? Something like that. Got it? So we would say, so for example, between 0 and 5, we shall take, for example, 100 points, for example, say. Okay, so that is done through this function. Okay. Okay. So I'm saying that I want Python to calculate the frequency response for frequency omega between 0 and 5, and I want it to take 100 points between 0 and omega, because you can understand what I'm doing, right? I'm numerically computing everything, and since I'm numerically computing everything, I have to figure out the particular points at which I want to compute everything, right? So this says start the value of omega at 0, end the value of omega at 5, and take 100 points including 0 and 5. Take 100 points in between them. Take 100 divisions, right? 100 points, 100 small points there, and compute everything accordingly. That's the value of omega, right? That's the value of omega. All right. So what is the amplitude response? I'm calling that giving it a variable name. I'm calling it amplitude response. So what is the amplitude response? The amplitude response is h called with this omega. Now if I call h, this function, with this omega value, then what happens? For each of these values of omega, so omega is now an array that contains numbers from 0 to 5 and has 100 points in it. Okay, so I have divided the interval 0 to 500 into 0 to 5 into 101 points. So we have 99 intervals, so that we have 100 points here. Okay, so you get the point, right? Get the idea. And we have to define the value of r, say r was equal to 1 and c was equal to 1, right? This is how we call the function. So now we are saying let's figure out the amplitude response by calling that h function. Okay, calling that h function and passing in the range of frequencies for which I want to calculate everything. But we are calculating the amplitude response, so everything has to be the absolute value, right? We are taking the mod is absolute value, so abs is the function, that's the absolute value function, right? So if I do something like this, all I have done, I have computed the value of omega, value of the amplitude response for all these values of omega, right? For all these values of omega. But again, before I can jump into this, let me show you what I mean. So if I say omega equal to linspace 0,5, and if I say 11 points, and let me just print omega. Okay, this is how you print in Python, right? Print and write something. Okay, so look very carefully. If I say linear space 0, 5 and take 11 points, then what happens? Between 0 and 5, it creates an array that starts at 0 and ends at 5. And it takes how many points there? It takes up 11 points. So we have got an interval of 0.5, right? So omega gets a value of 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5, 4, 4.5 and 5. Such. Okay? You get the idea, right? So here, similarly, I am creating an array that has 100 points in it, and omega value starts from 0 and ends at 5, right? Of course, the unit is radian per second. All right. So that is what we have done. So we have calculated the amplitude response. Now all I have to do is to plot the frequency versus amplitude response plot. All right. So now all I have to do is to plot the frequency versus amplitude response plot, and that's it. That's it. That is what you have to do. So if I run this cell again, you can click on this, or you can hit Shift Enter in your keyboard. You can hit Shift Enter in your keyboard, or you can just hit this. Okay. So if I now compute this, see, this is the frequency response we saw. All right. Let's change the frequency. Frequency range a little bit. So instead of say up to from 0 to 5 radian per second, say 0 to 3 radian per second, and do the same computation. So I edited that and reran this. Okay. So as you can see, now we have the frequency response of the particular RC series circuit as a low pass filter, right? So this is frequency and this is amplitude. But you know what? We don't see that the term frequency written here. We also don't see amplitude written here. Let's take care of that. Let's take care of that. After plotting the amplitude, let's say I want a label on the x-axis. So I would say x label on the x-axis, and let's say this is frequency, and this is in radian per second. So the label along the x-axis or the horizontal axis would be radian per second. Frequency, radian per second. Okay, and we shall have a label on the y-axis, the vertical axis. So y label, let's say this is the amplitude. Okay. Oh, what did I say? Now if I just do the plotting again, it says amplitude here, it says frequency in radian per second. And now you can see this is the low pass filter. This is the low pass filter. Why? Because it allows low frequencies pass in with a higher amplitude. Okay. And as the frequencies increase, what happens? The amplitude gradually decreases. Right? Do you see that? This is the low pass filter. It's a low pass filter, right? So this is the low pass behavior of the particular circuit we had. All right. This is the low pass behavior of the particular circuit we had. Right? Now, you asked that, okay, what if I change the value of R here? What if I want to change the value of R here? So say instead of 1, say it's 0.5. So do that. Let's do that. Now see, the behavior has changed slightly, but how slightly? As you can see, the curve has kind of flattened. The slope has changed. And we shall draw many plots all at the same thing shortly. So we shall see that. Okay. But in any case, try to understand that we have changed the slope of the plot. Yes, the coding for Python is actually really very simple, right? But again, let's talk about our signals and systems again. Okay, and again, just to show you, when I started with this, okay, and again, let me delete these. Delete selected cells. Okay, when I started computing with this, okay, it says populating interactive namespace from NumPy and Matplotlib. So NumPy is the library I talked about. So we're actually employing NumPy and Matplotlib. Matplotlib is for plotting, NumPy is for doing the numerical computations. Automatically everything is being taken care of for you internally. Okay, so NumPy was developed by Travis Oliphant, who was a signal processing engineer. He has a PhD in signal processing. And Matplotlib was developed by John Hunter, who was neuroscientist. Okay, he also had a background in electrical engineering, of course. So you can understand many things in Python nowadays we take for granted are actually developed and contributed by people who had affinity towards signal processing, because these things were developed for those purposes. Okay, so in any case you have this, right? But say I want to see how things vary for different frequencies. Say if I say different resistance values, say if I have R equal to 0.1, how things vary. If I want to see that, see the nature has changed, right? The nature has changed. As you can see, it is still a low pass filter. It is still a low pass filter. It is still allowing lower frequencies to pass with a higher amplitude and higher frequencies to pass with lower amplitudes. It is still doing that, but its behavior has drastically changed. So we shall see how we can actually incorporate those in our plot. So let's go back to our plot, and again let's copy paste everything here. Surprisingly so, yes. Okay, now let's say I want to do the plot. So this is the amplitude response and this is the plot, right? The labels are not of much importance here. Okay, so, and just one more thing, if I want a grid here, maybe I want a grid here, let's do that. In the plot now we have a grid. Okay, in the plot now we have a grid. Okay, let's do a grid here. All right, so now let's say I don't want to just see the plot for R equal to 1, R equal to 0.5, R equal to 0.4 individually. Maybe I want to see the plot of the frequency response, okay, or the amplitude response for varying values of R on a single plot. Okay, so I want this plot to be done for me and everything to be plotted here for different values of R on a single plot. Okay, I want to do that. So what would I do? I would run a for loop on the plot. So I would say for R in range. So R in, say for example, R in linspace. So again, try to understand what I'm doing here. So for R in linspace, let's start with a value of 0.1 and end at a value of, say for example, 1. And let's take how many points? Let's take 10 points. And putting a colon, and I'm hitting a tab here. Now here I am saying R is equal to R. Now see what is happening here. Now try to see what is happening. So how many plots am I doing here? I am actually doing 10 plots. I am doing 10 plots. And how am I doing 10 plots? I am starting the value of R from 0.1 and increasing with a value of 0.1, so that I have 10 points between 0.1 and 1. So what I'm doing, I am first selecting the value of R to be equal to 0.1, okay, and doing the plot, calculating the response. So here R is 0.1, okay, and doing the plot. And then in the for loop, the next value of R will be 0.2, okay, and I'm plotting that. Then the next value of R would be 0.3 and I'm plotting that. Then 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1. So I varied the value of R from 0.1 up to 1, and I am now plotting the frequency responses, okay, onto the same plot. And let's change the range of frequency. So instead of being from 0 hertz, 0 radian per second to 5 radian. So I think we are back. Right, I think we are back. All right. So again, that's the beauty of this Google Colab environment. What happens is, if the internet connection abruptly breaks or something like that happens, okay, all changes are saved. So what essentially happens is that you have everything saved, just like a Google Doc, right? But there is a red symbol here which says All right, so this is becoming really, really stupid, right? Like so many reboots of Terminator. This is like happening again and again. So I have to say, once again say I am back. All right, so we have finally been able to actually plot the responses, the frequency responses, okay, for varying values of R, right? So this is again, here R was equal to 1 and here R is equal to 0.1, right? So this is 0.1, R is equal to 0.1, 0.2 and everything. So let's change the frequency range. Let's instead make this 3. Now I have to constantly monitor whether the network is working or not. It's working, right? All right. All right. So let's look at the behavior of the system once again. Okay. So look carefully here. What is happening? What is happening is that if I have a higher value of resistance there, okay, this is R equal to 1 in that particular scenario. If I have a higher value of resistance, what is happening is that the thing that is happening is that the slope is decaying very quickly. Okay, the decay is happening very quickly, right? So here again, all these are low pass filters. All these are low pass filters, but if I have a higher value of resistance, then the decay here is happening quickly, right? All these are low pass filters, understandably, right? All these are low pass filters except if I have a higher value of resistance, then this decay is happening quickly, okay? But it is still again acting as a low pass filter, so lower frequencies are being allowed to pass, higher frequencies are being stopped, okay? Kind of have a smaller amplitude here. This is based on the value of R that we have here, right? So feel free to ask any question that you might have. Some people might have been booted off from the live stream because of the thing that is happening, network issues. Please join back in if you are still following up to this point. I've just refreshed the stream just so that I get to see everything back. All right. All right. So I believe this is understood, right? This is understood. Okay. So with that said, let's go back. Let's now again copy paste our definition of the frequency response here. Yeah. Okay. Now let's talk about the RLC series circuit, right? Let's talk about the RLC series circuit. Now let's, instead of calling this H, let's call this HRLC. Who knows? Something like that. That's the name of the function. Okay. So now we have one other thing to deal with here. Okay. So here we have that. Okay. So what was the frequency response of this? If you recall, I shall have to bring it back. What was the frequency response of this? What was the H? So this was j omega c divided by j square omega square LC. Okay, okay. All right. So return j. So this is 1j omega c divided by, so j square omega square. So I can say 1j omega square. So in Python, square is just double star. So power is double star, right? Omega square LC L star C. Okay, right? So this is j square omega square LC plus, then let me just go back once more. This was j square omega, so j omega c divided by j square omega square LC plus j omega RC plus 1, right? So basically I have now j omega RC plus 1. So This is my function. Now, of course, I have the liberty of putting whatever value of R, L, C I want here, right? So again, I just change the name of the function to HRLC just to satisfy myself, something like that. Okay, I could have written R. I could have written anything. Donkey Kong. No. Say for example 12 to the power 3. This double star is to the power, so that's 12 cube, right? That's 12 to the power 4. So double star is to the power. Okay, so that's 12 square. So double star is that, right? That's 12 to the power 10. Got it? Not 3 stars, 2 stars for everything. 2 star is the power, symbol for power, exponentiation. Okay, so I think you got that, right? All right, so here we have defined the frequency response for RLC, right? Frequency response for RLC. Let's now copy paste this. Okay, now of course we are not calling the H function, we are calling HRLC function. This is the function, and we are calling with a value of omega that varies from 0 to 3, and that has a value of R. We have given the value of R. We shall also have to give the value of L. All right, so that's, yes, the caret symbol. This is the caret symbol, right? Often used in many programming languages to denote power, right? So in Python, this is double star. Okay, that caret symbol has become a power, double star. The caret is used for bitwise XOR in Python. Yeah, just forget that for a moment. So now we have the frequency response for, rather the amplitude response. Okay, because we are calculating the amplitude response. See, this is how we defined the function. We passed in the value of omega, then we passed in the value of R, L, and C. Here omega is an array. R, L, C are constants, but omega is an array. Okay, and omega is an array. So here we can see that omega has this value. Okay, starts from 0, ends at a frequency of 3 radian per second, and we are just calculating the amplitude response. Let's plot that. Okay, so that is the amplitude response of the system. All right, so what kind of system is this? What kind of filter is this? Try to understand. If I pass in low frequency, let's change the range. Let's change the range and make it like say 5. Okay, what kind of filter is this? Okay, this is kind of a filter. This RLC series circuit is kind of acting like a filter, that if I apply low frequencies, so if I send low frequency sinusoids, what happens? It is blocking them, right? Because the amplitude will become very small. The same thing will happen if I pass in high frequency sinusoids. It is still again going to block them. So if I pass in low frequency sinusoids, it is going to block them. If I pass in high frequency sinusoids, it is also going to block them. Right? But if I pass in sinusoids of some intermediate frequencies, it is going to let them pass with small modification in amplitude, right? Very specifically, if I pass in a 1 radian per second sinusoid here, what would happen? The sinusoid will pass in, sinusoid will become, so the output will be, yeah, it's not called a medium filter. Okay, the output will have an amplitude of, the output will have the same amplitude as the input. The phase angle will change, of course. The output will have the same amplitude as the input, for example, in this scenario, right? And if we pass in frequencies that are, pass in sinusoids of frequencies that are closer to this, okay, they will have smaller reduction in amplitude. But if I pass in high frequencies, okay, those sinusoids will have again large reduction in amplitude. If I pass in low frequencies, those sinusoids will also again have large reduction in amplitudes. Okay, so this filter is known as a band pass filter. So it is allowing a certain band of frequencies to pass, and anything that is lower than that particular band of frequencies is being blocked, Anything higher than that particular band of frequencies is also being blocked. So this is known as a band pass filter. Okay, this is known as a band pass filter. Okay, this is allowing a band of frequencies to pass, okay, with small modification in amplitude. Okay, if the frequency is higher than that smaller band, so for example, consider the band to be between a very small value here and a very small value here. Okay, so any frequency that lies in between these, okay, will be allowed by the filter to pass with some small alteration in the amplitude. But if the frequency is way beyond that band, what happens? It's blocked. Okay, if the frequency is way below that band, it's also once again blocked. Okay, also once again blocked. Is that understood? Is that understood? Right? I think this is understood, right? So again, feel free to ask any question that you might have. Okay. Now let's change the value of R and see how this actually looks like. Okay. We have the same thing. Okay. Now let's take this. Okay. We did the for loop and change the value of R and plotted everything, right? All to the same plot here, right? Let's do that here. So we have that. Now we are going to call this HRLC function, and R is equal to going to be R, L is going to be equal to 1, and let's change the value of C here, and let's, instead of say this is, make this 5, let's make this 5, and instead of saying, say we are starting from 0.1, let's start with 0.2 and end with say 1 point, what should I say, 1 point, how many, 1.5, 1.6, 1.6, something like that. Let's plot that. Okay, let's plot that. Okay, let's take slightly more number of points because things are becoming jagged edges. So let's take more points. It does not matter. Okay, right. So this is again now. Okay, this is, let's, with plots you can do something slightly more interesting. Let me just do an advanced Python trick here. Okay, I'm putting a label. And that label is going to be a Python string. I'm doing something slightly, what should I say, slightly advanced in here. So let's, that will be understood, I think, later on. Okay, so point, let's do that. Hold on a second. Huh? Again, you don't have to be worried about this, what I'm doing here. Okay. All right. So now we have a color coding for this. Let's say R equal to. So now we have legends, right? So now along with the plot, we can see which color represents what. Okay, so this one is representative of R equal to 0.2, right? The next one is representative of R equal to 0.36 and so on, right? So I increased up to R equal to 1.6, something like that. Okay, so with that said, as you can see, as the value of R increases, what happens? This peaky nature is kind of being decreased, right? This peaky nature is kind of being decreased, and what is happening? Okay, this is still acting as a bandpass filter. Try to understand. This is still acting as a bandpass filter, and the frequency band is still around 1. The frequency band is still around 1 radian per second, right? The band of frequencies this system is passing is still around 1 radian per second. Okay, but look carefully. How is the amplitude changing? All the slopes and sharpness of the slope and everything that is changing with the value of R. Okay, those things are changing with the value of R. And again, we shall discuss everything properly. Okay, but again, notice very carefully that this 1 radian per second, this frequency is the frequency at which the amplitude of the output signal has the maximum value, right? This is the frequency at which the amplitude gets the maximum value in the output, right? This frequency is known as the corner frequency. This frequency is known as the corner frequency. Okay, and this is also the frequency at which something called the resonance happens. Okay. Well, someone is asking, sir, it is not seems that the value of R is not increasing in a similar. Okay, because I took only, say for example, 10 points between 0.2 and 0.6. I could have taken like 15 points. I could have taken 15 points. Maybe if you're not 15 points, so what should I say? 12, 14, 16. So I could have taken 8 points. Say if I take 8 points, between those, now we have this. So you have to just figure out how many points you want. Right. I calculated 10 points, so it divided the interval in 10 divisions, right? So accordingly, we had some other values. So here we have this. All right, the point is that the frequency at which the amplitude of the output is maximum possible, so the amplitude response is maximum, is known as the corner frequency in this particular case. And in this particular case, the corner frequency would be 1 radian per second. Okay? So in this particular case, the corner frequency is 1 radian per second. Got it? The corner frequency is 1 radian per second. And as such, we shall quickly later on see that the corner frequency is determined by root over 1 by LC. Okay, and this is also for the series RLC circuit is known as the frequency of resonance. So this is denoting the resonance frequency. Okay, for that particular circuit, this is also representative of the resonance frequency. So let's do one other plot here. Okay, and here now I'm going to change the value of L. I'm going to change the value of L instead of changing the value of R. I'm going to change the value of L. Okay, I'm going to change the value of L, and I'm going to change the value of L from, so R is going to be 1 here. And L is going to vary from 0.2 to 1.6. Yeah, and accordingly, we shall see now a certain different behavior is happening. We shall see, and let's plot it. Let's plot it. Okay, instead of saying that, let's plot it. Right? Now we have different varying values for L. Right? Now as L is changing, okay, again look very carefully. This is for L equal to 0.2. Okay, and this one, this sharp one here is for L equal to 1.6. Okay, so what you can see here is that the frequency at which that peak was happening is now changing. The frequency at which that peak was taking place is now changing. So the band of frequency it is allowing to pass is now changing. Okay, so the resonant frequency is changing. Okay, but the amplitude at resonance frequency is not changing. Right? Previously, because of the changing value of R, how much damping was happening, how much amplitude was changing, that was determined by the value of R. Now by changing the value of L and by changing the value of C, similarly, you will see that the frequency at which the resonance is happening, namely the corner frequency is changing, nothing else is changing, right? This is still a band pass filter, okay, but what band of frequency it is allowing to pass, okay, is now shifting, right? Here, what band of frequency it was allowing to pass was shrinking or enlarging, right? So here for this filter, the band of frequency it allowed to pass shrinked, right? Here for this one, the band of frequency it allowed to pass was larger. Okay, so band of frequency it allowed to pass or stopped, okay, was shrinking or enlarging, right? Expanding. Here the band of frequency it is allowing to pass, okay, it's shifting. It is shrinking and becoming it is shrinking, and sometimes it is becoming larger, but it is also shifting, right? It is also shifting because of the value of L, changing values of L and C. We can see a very similar thing if I change the value of C, okay, and plot it. So you can see we can do all these computations using Python very quickly and very easily, right? And we don't have to have a very good computer. We don't have to install anything. Just by means of using Google Colab, we can have this, and I can now share this file with you. just how I share this, right? I have a share button here. I can share this with you, and you can open this with your Google Colab and tweak these values and see how things change. Maybe break it, right? Before you can make it, you should be able to break it, right? As engineers. So we shall continue our discussion. It has been long enough already. It's been 2.5 hours already. So we shall continue our discussion on the next class, and we shall see how we can understand these things with slightly more details into it. But in any case, from the next class, we shall not be computing anything manually. We shall be using our computer to do our computations. Okay, and as such, this will be the end of our discussion today. And feel free to ask any question that you might have. Again, I shall, after the end of this stream, I shall share this file with you, and you can open Google Colab and you can do all the computations. And again, we shall end our discussion with a computing platform. And again, Techno India is currently introducing a new course called Computer and Electrical Engineering. Okay, and there will be a huge emphasis on computer related techniques, and I'm trying to employ some of those here. Okay. And I haven't taught you Python programming at all. Okay, I have just used Python as a tool here to do my bidding here, right? So, right, we wanted to do computations, and we have done computations, and we shall have classes on Python programming. Okay. Again, our objective of whatever I learned, whatever we shall do using Python programming will be geared towards electrical engineering. Okay. And this is just one part of that. So I would encourage, after sharing this file with you, I shall encourage you to tweak different values. And if you encounter an error, okay, if you get a huge error or something, just mail me back. I shall check that error, and I shall teach you how to actually do these things by yourself. Okay. And again, later on, I shall show you how to do Fourier transforms here, how to calculate the step response, a response of a circuit or system with any arbitrary input, do all the signal computations. So previously, I used to show you demos, different demos I used to make. And again, those demos are kind of advanced Python programming. Okay. So now here, you shall be able to make your own demos, and you shall learn how to make your own demos. All the calculations you shall be doing using Python. And again, so that will be the end of today's discussion, and feel free to ask any question that you might have at this point. Otherwise, we shall end our discussion at this point. It's been a very long class. So thank you for being here. Again, if you have any query, feel free to ask. I'll be waiting here for just one more minute. Oh, question is how much syllabus is left? I mean, we shall have 1 or 2 more theoretical classes. We shall have 1 or 2 more theoretical classes. Then we shall have classes on Python programming. And just to let you know that the end of theoretical classes is not the end of the entire subject, right? We shall have classes on Python programming related to our signals and systems classes, and so that we have a computational tool ready with us that we can employ anywhere we want. Okay, we shall learn how to deal with the things we have learned in our entire course programmatically, right? How to write programs for signals and systems, to analyze signals and systems. How we can do that using Python, we shall learn those later on. Okay, we shall have like 1 or 2 more theoretical classes. So as far as the theoretical classes are concerned, we are kind of at the end. Again, just one more thing, the Python related classes will not be optional, really. Those will be counted as included in everything, right? In any case. And yes, if you have doubts, feel free to list them, and if I can answer them via an email, and if you get and if you can understand those, that would be nice and all. But if you require additional classes on topics that we have discussed earlier, feel free to ask, and if I need to arrange additional classes for those, I shall. Okay, regarding topics we discussed earlier. So ask the questions via emails. If I can answer via email, I will definitely answer via email. And if it seems that I cannot answer via email, I shall have to make a video for that, make a live stream for that. I shall do that. In any case, regular classes are kind of at an end. We shall lead 1 or 2 more classes, maybe just one more class. In any case, feel free to ask any question that you might have. And actually, this subject is going to be continued on the next semester by the name Control Systems Engineering. Okay. This subject is going to be continued on to the next semester. Yes, this subject is going to be continued to the next semester in Control System Engineering, and there we shall see Laplace transform. Okay. And there, again, we shall start everything from scratch. I shall not just tell you the formula and ask you to solve problems on that, right? And we shall learn why Laplace transform is important along with everything, right? Okay. Just to give you a hint, so we have already talked about the sinusoidal steady states, right? So if I want to analyze the transient states, okay, then the Laplace transform becomes very important to analyze the transient states, right? So we have steady states, and whatever happens between 2 successive steady states, we have transient states, and that analysis of that will be the whole purpose of our control system engineering classes. And for that, we shall require Laplace transform. Yeah, actually, Laplace transform and Fourier transform are the things that you should be quite aware of and quite conversant on, right? You should have good, what should I say? You should have good expertise on Laplace and Fourier transforms, because you are electrical engineers, right? Right. All right. I could have talked about Laplace transform in this semester, but that would be kind of out of place discussion. Okay, so we have moved everything onto the control system engineering classes. Okay, and that will be just a continuation of whatever we are dealing with here. Okay, that will be a continuation of this subject. Okay. So in any case, this is going to be the end of discussion for today. Feel free to post me any question that you might have. And if I think I need to arrange additional classes on the topics that we discussed earlier, we shall do that. And in any case, we shall need 1 or 2 more classes on new things, and we shall discuss a few more things apart from that. Okay, then we shall have classes on Python programming, specifically targeted towards signal processing. And no. So one of you are saying that in control system you don't have anything other than transforms. No. That's not the case at all. Okay. In control systems, in modern control engineering, you don't even have transforms. Surprisingly, we deal with everything in time domain in modern control engineering. Okay. In modern control engineering, nothing happens in frequency domain. Everything happens in time domain, and there are certain analysis techniques that we can employ to analyze everything from inside time domain. Okay, so there is a very strict assumption here. The strict assumption is that the system has to be linear and time invariant. In reality, most systems are time invariant but not linear. So if we have linear or non-linear systems, okay, we cannot apply any of the transforms. We cannot apply Laplace transform, we cannot apply Fourier transform, anything, because those assume linearity of the system. Okay. And then we shall have techniques based on vector spaces, linear algebra and vector spaces, that will help us analyze the systems that are not linear in nature. Okay, so transforms cannot help us there. Okay, so we shall do this in the next semester. So that's by that time I will believe you will forget everything I have taught you here. Okay, that is what happens, right? In any case, that will be the end of our discussion today. Thank you very much for being here, and I shall see you on next Wednesday. In any case, feel free to ask any question that you might have. And again, let me remind you about the homework. The homework is to figure out the RL series circuit with a different configuration. For the RL series circuit we did today, we measured the voltage across the inductor. Okay, for the RL series circuit, you are supposed to do, you have to measure the voltage across the resistor, right? And see that acts as a low pass circuit. So figure that out. And I would encourage you to do some Again, I talked about vector spaces, but again, I shall elucidate the things as far as practicable. Okay, I shall not just tell you some ad hoc definition and ask you to do your computation. Right? And again, I will encourage you to do the Python programming and check a few things by yourself. All right. So thank you very much, and we shall end our discussion today. Stay safe, and we shall see you on Wednesday.